able to ride through transients, whatever, maybe not that, not that complex, but be able to say we want to stress the insulation in order to provide a meaningful look into the health of your equipment, right? And the analogy is, I used this before, right? The garden hose that has a pinprick in it, right? You have a leak in your garden hose, but if you're not cranking that thing full blast in the summer, that's when you're going to find out that you have a hole in your garden hose, right? So until you subject it to a high enough pressure, you're not going to be able to expose those faults within your system. So same kind of deal, right? And if you're able to get that point across confidently and comfortably, well, I'm going to know that you are, you're doing well on your final exam. Cool. All right, so let's take a look at our textbook. So by now we're in week 5. So I trust that everyone, question mark, has their NEET MTS book?
Yes, but I forgot it.
That's all right. So we'll follow along here. But definitely, you're going to have it. You may not have class on Thursday, but I know you're going to be cracking the book on Thursday night, right?
Yep.
Okay.
Always.
Good stuff. All right. So I think I got your NEET MTS 2023, hopefully. And some of you may have the 2019 if you took it. Yeah, Miguel, you might have the. Oh, you're good. Yeah. So, take your NEET MTS book and we're going to take a look at the relevant sections here. Always start at the table of contents just like our NEC course. So, because we are looking at tables, we'll walk before we run. Let's take a look at our tables, low voltage, low energy. That was a reserved section, so that's actually in progress. Right? But let's go to page 40, or whatever version you may be running. Cables, low voltage, 1000 volt maximum, right? Which actually may be along these lines, right? Of course, they don't normally run at 1000, maybe they'll be a 120, 208 kind of thing. But they're actually rated for usually up to 600 volts. So, 1000 volt max, let's start with here. And again, for some of you, this will be not the first time you've opened up your NEET MTS book. We've looked at other sections in the past, circuit breakers from Thursday, also the transformer and switchgear sections. We've taken a look at those. So you'll see some familiar themes, familiar progressions, but in this case, definitely this class is concentrated on the cable sections. One thing I want to know, by show of hands, with 2019. Yeah, that's actually good because I'll talk about it in another class, but between 2019 and 2023, there's actually a very, very significant update to the cable section. So the good thing is we don't need to worry about that because last time around I was teaching this class. There were a lot of discrepancies between people who had 2019 versus 2023. But definitely that means we can go full steam ahead with the 23 version. Right? So if you're looking along here, take a look at how the progression goes. So 7.3.2 is your low voltage cables, 1000 volt max. You'll see A is the first header for visual mechanical inspection. Before we even go into a deep dive there, you'll see that B is for your electrical tests. C is for your test values for visual mechanical. So C is kind of the answer to A. And then you'll notice that D is the answer to B right there, right? So it's test values, electrical. So visual mechanical, electrical, test values for visual mechanical, and then test values for electrical. Again, this is just to give you the overall sense of how this book is trying to, give you almost a procedure, right? Influence your decision making to be able to allow you to perform your electrical tests that are necessary for each component. Right? So let me take a wild example here, and I'm just going to go to random section. Right? Spin the wheel, spin around 10 times a point. Now we're looking at direct current system batteries, valve regulated lead acid or VRLA type. Right? This is not a battery class. But you'll notice that even for an unrelated piece of equipment, and those of you in the other classes have seen this in the transformers and the switchgear section, it follows the exact same progression here, where A is visual mechanical inspection, B is your electrical test, C is your test values for visual mechanical, and then D is your test values for electrical. So we don't need to play that roulette game again, save that for Vegas 29, right? I guarantee whatever apparatus you end up on, switch is SF6, that's your sulfur hexafluoride, visual mechanical, electrical, test values for visual mechanical here, and then your test values for electrical. So there's a reason for that, and it should be consistent, right? Consistent, repeatable, that kind of thing. But the reason for that is that visual mechanical inspection should be your first thing you do, right? We don't often think of, when you say your tools at your disposal in the job, on the job site, your eyes, your ears, even your nose if you're smelling something burning, right? That is your very first inspection that you perform, right? Just like the, and I think Jeffy pointed out that video wasn't working in the 256, but it's that classic video of the guy sniffing around near the loading bay as you see explodes in his face. Had he been a little more judicious in his approach, he would have known that that fell under NEC, as they call it, signs of imminent failure, right? If you're smelling something burning, one sniff's enough, right? Get out of there. But I guess he wanted to pinpoint it using a very scientific nose and blown up in his face. So, there's a reason that A is going to be your first inspection you perform, visual mechanical. Let me get back to low voltage, right? So, let's take a look here. Inspect exposed sections, cables, and connectors for physical damage and evidence of degradation. Maybe heating, like that example we saw, right? Maybe exposed copper where it shouldn't be. If somebody's been pulling cable, right, it got hung up in the corner, right? If you weren't using, the proper tools in order to pull that wire, you could say, man, I spent the past few hours pulling this one. No one's going to notice this little thing. Well, it happens, right? So, but that's another reason why we come into play. So obviously the stakes are higher, say a refinery application. Sure, they spent days pulling large cable through a conduit. So just to give you the real world example, we'll get a large spool of cable, kind of like this one, but much bigger. Say about the diameter of the top of that bench right there. So large spool of cable, very large cable. We'll have some examples floating around the class throughout the semester. But the cable arrives on site, right? That's where we come in and we test it. Did the customer get what they paid for? This thing might have been trucked in from Montana or up north, or Georgia, where they have a large cable contingency there, right? So this thing, through all terrain, through all across America, maybe it hit that ice storm in Atlanta that delayed me for a few hours. How do you know that the cable is going to be in the same condition that it was when it came off of the assembly line or the manufacturing line, right? So it's our job, as a large refinery, Matthew's going to say, hey, Maricon's, calling Tony D. Maria to test this cable on the spool that came off.
Never tested anything like this.
We don't name names here.
They did visual inspections. Oh, we saw a nick, and then they'll stop it.
Visual mechanical.
Yeah, but that was it. No testing.
All right, we don't name names, but Schultz.
Medium voltage.
0 out of 5 stars.
5 kV stuff. Never tested.
Do not like and subscribe.
Just pull it right in.
Like it for you, I know a guy. Okay, so definitely, as we said, I'll call it back to the physical condition of your electrical equipment is going to directly translate to the electrical performance. So, I don't know about you guys, but when they start up that circuit, I'm going to be behind that. So, I'm going to be behind the Schultz supervisor. Oh, Mr. Schultz, there you are. I'm going to be behind you when they show that switch. So visual mechanical definitely first stop. And so after they pull the cable, they're going to test it again, right? Did something happen as they were pulling the cable? And we ran into some dicey situations where people can assure nothing happened. We'll say, hey, the data speaks for itself, right? Fortunately, humans lie, but numbers don't lie. That's why I like numbers. So you're going to, especially when you're the one who's going to go up against, say, Schultz, for example, you're going to say, hey, listen, those guys might tell you they did a good job, but I have to test data to speak to them.
Something can happen inside the conduit where you couldn't see it.
Absolutely. Yeah, and I don't know, it might have got run over by a forklift. That happened. We've seen it. So that kind of thing, anything could happen in transit, right? So that being the case, that is exactly why you, as the qualified test technician, are so valuable, right? Before they waste all the hours, right, all the labor hours pulling the cable in the first place, you test it on the spool. You identify a problem before they even go down that route. So, and then, so you'll pull the cable, You'll test it again to make sure nothing happened too bad, or it's within specs rather, because something always happens, right? There's friction, there's unexpected issues, but something happened, but how bad? That's the question. So that's why we talk about, is it within specs? Because there is permissible error. We're human, right? And we live in the real world. Right? And then by the time they hook it up, commission it, do terminations, right? Land those connections. We'll get to what all that means that I just said. But we test it again. We do our final test before anybody ever pushes the other red button. Red button that makes millions of dollars per hour. So yeah, there's a reason why you get a crumb off of that plate. You're living a comfortable life as a team test technician, right? Because there's so much at stake. Everybody wants a piece of that pie. I think, what was it? This was already signed a few years ago, but the whole electrification of the port and the whole EV movement and stuff, California earmarked like $1.2 trillion for like the green initiative. So again, if you get 0.001% of that $1.2 trillion, man, you're getting a Malibu mansion or something like that. So for us mere mortals who can't even comprehend what $1 billion is, and give you a speck of that $1 trillion plate. Right? So that's why I provide real world examples to say, what does this actually mean for you? What is the value proposition of where you'll find yourself in this industry? Right? So, expect when we run into each other over some beverages, perhaps in Vegas in 3 years, you're already fully fledged, maybe need a level 2 technician at the time. Definitely looking forward to hearing some of the stories that you encountered, right? I mean, seeing where what might have happened to your cable in the last job. So by the time we get to B is electrical tests, visual and mechanical, there's no sign of imminent failure, whatever it may be. You perform your electrical tests. And thanks to Irfan and all of you hammering at home over the past few weeks, what's this one here? Perform an insulation resistance test on each phase conductor with all other phase conductors grounded. The applied potential shall be 500 volts DC for 300 volt rated cable and 1000 volts DC for greater than 300 volt cable. Test duration shall be 1 minute, and I'm sure he repeated exactly why we talked about that 1 minute time frame. Remember, science is both quantifiable and repeatable, right? We quantify how many volts we subject it to, and is repeatable at 1 minute. So we have a data trend that can be looked at year over year to say, you're going to have to escalate your 5-year PM. You might want to think about testing it yearly, right? If the numbers change after that, hey, listen, we're going to want to test this every 6 months. And if you get any closer than that, then you may say, hey, during the next large turnaround, you might want to take this section of the plant out of service so we can change out, your fried cable. So C, test values for visual mechanical, compare bolted connection resistance values to values for similar connections. Investigate values which deviate from those of similar bolted connections by more than 50% of the lowest value. So that is what we're going to be talking about today, along with our bolt torque, connector torque levels. In this case, they're small wires, so usually, you won't always torque your low voltage screw connections, but you might. And number 3 is going to be a thermographic survey. So keep in mind, you're going to see these 3 come together: your ductor, your torque wrench, and your thermographic survey. Those are kind of the big 3 of electrical connections. We're going to see that time and time again. Right? So in this case, for low voltage, 100.1 is even beyond the scope of low voltage. But here it says insulation resistance value should be comparable to previously obtained results. Right, that's our data trend, and similar circuits, but not less than 2 megohms. So, of course, if you recall your 100.1, there was no column showing 2 megohms. But this is going to be a reference for low voltage testing, which within the next week or 2, we're actually going to be doing. So keep this one in mind. Right? And then again, here's our 50%. See, I circled it. So hopefully all of you have this kind of noted or in the back of your mind, ready to go on today. But 50% is going to be the magic number. As we move to our shielded cables, medium and high voltage, right? So we're going to see similar themes, starting with visual mechanical, going on to our electrical tests, going on to the test values, visual mechanical, and finally our test values for electrical, right? So that takes it from, okay, how do we obtain this data? And then second, what does the data mean? What are the conclusions we can make from it? All right, so this is the full picture. End to end, you should be able to determine a lot about the health of your conductors from these things. Right? So visual mechanical, it's inspect exposed sections, right? Inspect terminations, splices, bolted electrical connections. What we're interested in here is the electrical tests, right? Because we're talking Megger DLRO, Megger Conductor. Perform resistance measurements through bolted connections with a low resistance ohm meter. That's the LRO. That may be analog. Certainly recommend digital. So digital low resistance ohm meter in accordance with section 7.3.3.8.30.1. We'll show that one a little bit later. Perform, actually A, that would be part of your visual mechanical inspection. So 2, perform an installation resistance test. And this one references table 100.1, which you're all very familiar with. Apply voltage in accordance with manufacturer's published data. This is what I mentioned very early on, and then you're going to see this a lot in pretty much all the sections that say NETA will defer to the original manufacturer. Again, they are expected to be the utmost authority on their own equipment. But in the absence of that, where we find ourselves in this class, that's when we use 100.1. Perform a shield continuity test on each power cable by ohm meter method. We're definitely going to do that a little later in the semester by the time we get to medium and high voltage shielded connections. All right. So what we can tell is especially one and a bit, just over 1 page was our low voltage cable, right? But by the time you get to a medium high voltage cable, we're looking at 1, 2, 3 and change. So, into the 4th page, right? So as equipment gets bigger, and other classes have seen this, as transformers get bigger, as circuit breakers get bigger, there understandably will be a lot more testing to be performed in order to understand, the full extent of the equipment, right? And especially at high voltages when things are much more critical, when things can get a little iffy, we definitely want to test it in more ways with more complex testing methods. So if our focus is 7.3.3.8.1, let's talk about how to evaluate this data when we get it. We're going to get into all this good stuff. This is by the time you get to this type of testing for medium and high voltage testing, VLF testing, very low frequency dielectric withstand, as well as VLF tan delta. There are people who, online partial discharge. These specialists in these specific types of industries are very, job security, simply a non-issue. You can punch your ticket anywhere. You can work for anyone because this is very, very high-end, very complex stuff. And if you become very well versed in this one, you'll be highly regarded in the industry with a very specific skill set that is, highly coveted in the industry and very well compensated for. So this is going to be the tail end of this semester when we can go into, at the very least, the theory of each one. The benefit of having, say, Doble come in, Megger come in with their latest equipment is that they'll bring in, and we do sometimes, they'll bring in the dedicated testers for these types of tests. They run upwards of $50,000 just for the test set. So, for you future business owners, so the investment pays for itself pretty quick. It might sound like an astronomical number, but that's how much you're going to be making in a big picture. Spend money to make money. All right, cool. So by the time we get to evaluating our test values here, right, we take the DLRO, we go across ABC or whatever it may be. Compare bolted connection resistance values to values of similar connections. Investigate values which deviate from those of similar bolted connections by more than 50% of the lowest value. Okay, so we've seen this enough by now. We keep saying that we have to evaluate them for 50% of the lowest value. Okay, conceptually that's one thing, but putting it into practice is what's going to be the best way to understand what it is we're doing here to establish what is an acceptable value. Because that's what this is all about. Remember, the first set of slides said that DLRO should test that equipment has not gone above acceptable values. So this is our benchmark for what an acceptable value is. Right. So we're going to take actual numbers to it, and eventually, probably in this class at this time, we're going to get a set of values that we can actually apply the 50% rule to. Okay. So these are the relevant sections. Feel free to have those handy. Really in each lab that we're progressing through, especially by the time we get to the medium high voltage cables, this is going to be your field map to be able to perform the tests effectively and safely. All right. So next we'll take a look at this handout here, and the hint is that if you understand this very well, then you will get the 10 out of 10 that you so desire on this week's Canvas quiz. So, talk about digital low resistance ohmmeter, also referred to as a ductor, redefining current, right? So, why do we perform this test? Because measuring low resistance helps identify resistance. So you know it's the opposition of current flow. That have increased above acceptable values. We're seeing this again. What is an acceptable value? We're going to continue to answer that question. Operation of electrical equipment depends on the controlled flow of of current within the design parameters of a given piece of equipment. Ohm's law, which we've had plenty of fun with today, all right, will be the method for determining what comes out the other end of the equipment, what displays on the screen. Low resistance measurements are required to prevent long-term damage to existing equipment and to minimize energy wasted as heat, right? So we talked about damage that can result from high current, right? We talked about loose connections, right? We talked about short circuits. We also talked about energy wasted as heat. That was our I squared R losses, our Watt's loss. So B, how do we do it? We took a look at the circuit diagram. Here's another helpful representation. A low resistance ohmmeter uses two internal measuring circuits, and we already know what those are by now. Supply injects a current into the test sample through two leads, usually identified as C1 and C2, and the magnitude of the current is measured. Concurrently, two probes, normally referred to as P1 and P2, measure the potential across the sample. So the instrument then performs an internal calculation, this calculation, as we saw, to determine the resistance. All right, and so they don't show, the DC supply. They don't show the ammeters, voltmeters that were pointed out for us. But in this case, we are seeing where C1, P1 made contact and C2, P2 made contact, and we know that it is directly across the subject, right? We know that these made contact here because the calculation is only performed here. Anything upstream of that, aka the internal resistance of the leads, right? They could be short leads or they could be long enough to go to both ends of those transformers in the yard, right? So however long those leads are, it doesn't matter because we only care about that resistance across the, what the customer's interested in, the piece of equipment that he laid out before you. So also keep in mind, this section will be important to answer one of the questions that says, what is the function of C1, P1, and C2, P2? Which one, actually provides an electrical value and which one measures. All right, one's going to be the active, one's going to be the passive of the two. So keep that in mind. Setup of test to equipment. So this one actually shows, again, we're seeing the four probes here, the four connections. And in this case, they're C-clamps. I think earlier said the difference might be whether it's alligator clips or C-clamps or push probes, that kind of thing. But the exact kind of interface doesn't matter as long as, again, C1, P1, C2, P2 make contact at the specimen of interest. Right? So A is your value of variable here. Can be a circuit breaker. No surprise, it's 266 right there. Your transformer is 268. Motor, what are your other motor classes? Bus section, so you're 267. And we are here in 265. Probes to measure the resistance can be either alligator type push probes or C-clamps. We don't necessarily use C-clamps for the equipment we've seen here, but this is going to be perhaps a high voltage. If you had a high voltage connection that was maybe up high in the air or subject to the elements, then you'd want a more positive connection like C-clamps. But in our case, in a controlled environment, mostly we're going to be working with alligator clips and push probes. Expected values here. This is where we answer a question we've been asking all along, which says, what is an acceptable value? Again, in the absence of manufacturer specifications on what an acceptable value is, we're going to use the need of 50% rule here. So, if no values are available from the manufacturer, use the need of 50% rule, which is found by taking half of the lowest reading and adding that number to the lowest value. If that value is greater than the highest reading, then it must be documented and brought to the attention of the equipment owner. Right, are we all clear on that? Okay, so we're going to take examples in order to figure out what that means. All right. So the first example we're going to do, A phase equals 2 100 microns. B phase.
175.
Thank you. 175.
And last one is 250.
Plus 250. So, USD qualified electrical test technician. Boom, boom, boom. Good stuff. A phase, B phase, C phase. The good news is you got values. Bad news is, oh wait, I forgot to study the section that says are these good or bad. Right. So this is where we come in now. We say, okay, we got to sort of test data, or we don't just hand this to the customer and say, well, here you go, there'll be $10,000. No, that's not an accurate, that's not a real world situation. But if you find a customer like that, let me know. Okay, so you get this data, but what separates us from every, other non-NETA accredited companies or whatever? The reason that they pay a little more than those guys is because we're able to say, hey, is this good? Is this bad? More importantly, why? More importantly, if these are bad, what do we recommend as qualified test technicians to say? How can we improve the health of your system, improve the reliability of your system? So, the 50% rule states that you take the lowest value. Now, which of these are the lowest value?
175.
Lowest value here. All right. You're going to calculate 50% of this. Right? So 50%, 175 divided by 2 is going to be 87.5. So this is half. This is your 50%. So what do we do after that? We're not done yet, right? So we have to add it back to this value, right? So we're still dealing with B. B is the one that we identify and stick with. So we're saying 175 plus 87.5 is equal to
262.5.
262.5 microns. All right, what does this mean?
It's
I don't really know because there is no 262.5. Right? Now, so what this does is this provides your maximum acceptable value for red. Because red's scary. So, my max acceptable ACC value. Okay? So that is to say, if anything is beyond this value of your original set, then we have a problem. Well, why do we have a problem? Okay, mathematically, numbers don't lie. We like numbers. But what does this mean? If something was to exceed the 262.5, what does that mean? Is it going to blow up? Hey, stop everything, shut down the plant, try again next year. No, not quite. What this means is that there would be, you think of it as like undue heating, right? It would be far too inconsistent from your lowest value. Right? So if I were to, I love numbers and I love graphs. Okay, so I'm just going to make up a graph. Right? So you use a bunch of different colors. If you were to quantify it, you get like green. But what this says is that there is going to be an acceptable range of deviation from your purple. Right? Because similar to even loading on a three-phase system, right? We want even heating because load and heat, they go hand in hand, right? So if you're on a three-phase system, you take your clamp-on meter, and you're seeing one wildly above the rest, there's a problem. Right? Or you might see, the two outer phases have something, the middle one has nothing, right? Maybe you're single phase accidentally somewhere on the line, right? But we need to establish the acceptable criteria, right? And so all of a sudden, this green one is too high, right? That means that this is subject to more heating, more risk, and especially in the long term, because the 50% rule, like conceptually, comes down to we want consistency between three phases. ABC should be close. The question is how close? Well, how close is established by the 50% rule? Right? So we can talk numbers, we can talk graphs and stuff, but in words, it just means are the three values you obtained close enough to each other? That's what the 50% rule really means. All right? So in this case, if 262.5 is our maximum, what do we say about these? Thumbs up, thumbs down. Thumbs up. Because 250, even the maximum value, is still below 262.5. That means that they are close enough together, right? Because anything beyond 262.5 is too far, right? It's too inconsistent. We may have a problem. Make sense? Good stuff. Let's take another example. So, example 2, A phase, 200 microns. Cool, I don't have to rewrite that. Oh, saving me the trouble. 175 still good. Oh no, what is going on with C phase? maybe you tested this thing a year later, 2 years later, 5 years later, right? Maybe they only paid for 5-year PM cycles, right? That's good. All right, so this guy went up to 300, right? Which of these is the lowest value? Still the lowest value. Just been safe in the writing. I like that. So that means that still our acceptable maximum value is 262.5. So in this case, what is the major difference? 300 is too high. So you, as the qualified NETA electrical test technician, what can you conclude in words about C phase? What would you say? Let me take a step. Yeah, yeah. So it could be a loose connection because resistance goes up with loose connection. And the loose connection, what else goes up? Heat. And heat causes damage. Good, excellent. I'm loving what I'm hearing. Good stuff. And so as a NETA technician, you guys nailed it. You said C phase shows a possible loose connection and is outside of the 50%. Something like that is gold. Okay. So, example 3. Cool. So we've seen 2 cases, a passing and a failing condition, right? And from there, some of the others read in milliohms. Okay, so this is why your metric prefixes are going to be extremely valuable. I'll give you another example, especially for the digital ones, right? They may spit these out in different scales. So instead of, let's say, 0.3 million. And say, 0.3 is the lowest value. 0.3 is way lower than 175. So now we're going to conduct by 50% rule off this guy. So this is a base example to say you have to be able to represent them on the same basis, right? To do apples to apples comparison. Because if you're not making a correct comparison, then that means your conclusions could also be very wrong, right? So you may look the customer dead in the face and say, your equipment's no good, when really, you just didn't carry the digits or something like that. So don't be that guy, right? You're on track to become a qualified NETA electrical test technician. So consistent with your unit, right? Consistent with your calculations. And remember, 50% rule is going to be the threshold for your acceptable value. All right, make sense? Cool. And so with that, we're actually going to put this into practice. Remember, NEC states that you have to, have the knowledge, right? You guys have the knowledge now, right? You also have the reference material, right? But are you able to demonstrate the skills and abilities, right? And that's where we take this to the next level. Are you able to apply the knowledge that you've now gained, right? And in this case, let's find out. So I'll just get one representative from each row to come up, grab some food. And first